Continuing our tour of functions, we've started talking about somewhat general polynomial functions, going beyond quadratics, which are always going to be a really great home base. And we talked a little bit about the end behavior of those, and that'll come back in a few minutes. But I want to talk about a little bit of stuff they talk about in 3.4. One is just a really basic, nice qualitative fact. It's not numerical. It doesn't involve any calculation. It's that graphs of polynomials have these wonderful properties. They're continuous and they're smooth. We won't get real technical about that. That's a place for the calculus class, really. But it's pretty intuitive. Continuous just means that they can't do certain nasty things. You can't have a break or a jump. I created this as a piecewise function. It has a place where at x equals 1 where it suddenly jumps. It's got two pieces that are not connected. This is an example of a discontinuous function. A polynomial can never, ever look like that. Another thing they can't do, another kind of discontinuity, is blowing up to infinity for finite inputs. We will be interested in this as one of our last things to focus on, I hope, if we have time, with rational functions. Notice this is 1 over x. It's still simple algebra. It's even what you could say is a power function. We talked about that a little bit in the last video. But it is not a polynomial. Just because it's x to a relatively nice power, not a polynomial because it's not a positive or not a non-negative integer. So because these guys have really different behavior. You can't take 1 over 0, and if you take 1 over a small number, it blows up. Like I said, we'll be interested in those right now. The point I'm trying to make is that polynomials can't look like this. They can't have things where it zooms off to infinity. Again, you can see that the 1 over x graph has two disconnected pieces, and a polynomial graph will never have multiple disconnected pieces. The last thing is that it has to be smooth, not just continuous, but smooth, which is even a stricter restriction. And our great example of something that's not smooth is something that has a sharp corner. F of x equals absolute value of x. It's a lot of people's favorite function, I think. It's like this nice v. It's very symmetric. It's beautiful, but it's got a sharp corner right here. That is not smooth, and that's not something a polynomial graph can have. So polynomial graphs are continuous. They won't have disconnected pieces. They don't zoom off to infinity. They don't have any jumps, and they don't even have any sharp corners. They are always really nice, smooth curves. And if you think smooth, just what does that mean in real life? It really does give you the right impression. Continuous, smooth curve. And that's what a polynomial has to look like. So we've already discussed end behavior. I'll be reviewing that in a second in an example. The main thing is that that's determined entirely by the leading term of the polynomial. So you don't have to look at any complicated interactions between the pieces, the different terms of the polynomial. The y-intercept of any function ever is easy. You just plug in x equals 0 and you get the y value from what's the output of that function. We'll do an example in a sec, but I just wanted to say, hey, that's not a hard thing. Now, what's more interesting is the x-intercepts. And so sometimes we refer to those as the zeros of a polynomial because they're where the function outputs 0, where y equals 0, because that's how you know you're hitting the x-axis. So the graphical terminology is the x-intercept. So for example, here it's a little under 3, about minus 1 2/3 maybe. We'll do an explicit example in a second. So you can call them the zeros of a polynomial because it's where they output 0. You can call them the x-intercepts, and a terminology that's a little bit more specific to polynomials is we often call them the roots of a polynomial. So big theorem is that if you have a polynomial of degree n, it cannot have any more than n of these intercepts, zeros, roots, whatever you want to call them. It might not have all n that it's sort of allowed theoretically, but it can't have more. We've seen already for quadratics, they either have 2 intercepts, 1 or 0, and when they have 0 real roots, when they have 0 real x values that make them evaluate to be 0, it's actually because they have complex ones. And we'll come back to that in a couple videos. So how do we find these? It's the thing that we've done probably more than anything else. Set something equal to 0, use algebra to solve. So I want to just give an example where some of the work has been done for us already, because I want to point out what that says about the graph. and not get into really, really intricate algebra right here. So suppose somebody gives us a polynomial and they've given it to us already in factored form. That's really nice for what we're doing right here, because that's going to make it as easy as possible to actually set equal to 0 and solve and find those intercepts. So the x-intercepts, we're just going to take whatever the formula is for our function. It doesn't really matter what kind of function it is. We're always going to say, well, I want to find out where the y values coming out of that function are 0. So you just set the whole darn thing equal to 0, and you hope you can solve. Remember the zero product property. This is really, really review. 3 certainly is never equal to 0, but the other possibilities are that x plus 4 might be equal to 0. That's supposed to be a plus. And then this incredibly important word or x minus 2 squared equals 0. And that square is going to be a little interesting in a minute. Okay. Okay, well, but that's going to be pretty easy. Either x equals minus 4 or, and if you square root both sides of this, it seems like the square actually isn't doing anything. The only way that the square of a number can be 0 is if that number itself is 0, right? Oh, well, that's just x equals 2. Okay, so it might seem like, wait, does the square not affect anything? It does actually affect the shape of the graph. We'll see that in a second. But we've solved our basic problem. What are the x-intercepts? They're x equals minus 4 and x equals 2. While we're at it, let's get the y-intercept. That is ever so slightly harder in this form. If we were given it in sort of general or standard form with all the terms written out, it'd be easy. It's just the constant term. Here, we actually have to do a little bit of arithmetic to actually figure it out, right? So f of 0, I'm just going to plug in 0 into the formula and do the arithmetic. Okay, so that's 3 times 4, and then minus 2 quantity squared. Notice the minus sign goes away. That's going to be very interesting. And that turns out to be 48. Ooh, sorry, equals 48. Okay, so we're getting an idea very roughly what the graph might look like. It's going to hit the axis, no. It's going to hit the axis at minus 4 and at 2. That's the x-axis. It's going to hit the y-axis at 48. That gives us an idea of the vertical scale we're going to expect. Let's see. Let's look at the end behavior. Ooh, yeah, I already had that. The end behavior, ooh, I have to do a little bit more algebra. This is, again, where the factored form isn't that ideal. But let's just FOIL this thing out. Okay. What's that going to be? So that's going to be 3. I'm going to not do the 3 yet. This is a really good opportunity to just use our memorized formula for the perfect square trinomial. Then we have to get a little bit grungy. We're going to get an x cubed minus 4x squared. I'm going to go through this fairly quickly and hopefully get the right answer. So that's all using the x there. And then the 4, I'm going to get a plus another 4x squared. I'm going to get a minus 16x plus a 16. Collect it together. We're going to see that not all of this work actually had to happen. Ooh, minus 4x squared plus 4x squared. Oh, that's interesting. I didn't actually plan that. So that's just going to be minus 12x. So it actually simplifies kind of nicely. Okay. All right, so 3x cubed. Whoa, sorry. 3x cubed minus 36x plus 48. Aha, that's a good confirmation. That 48 is another way to get the y-intercept. It's pretty much the hard way to get it here. But the other thing that I cared about is what is the leading term, right? So it's got a positive leading coefficient and an odd degree. And so that's going to be the down, up kind of thing. On the left, it's going to be going down because negative numbers give negative numbers when you just plug it into that part, which is going to dominate for large x values. And positive numbers are going to give positive numbers. Okay, so I'm going to give you the computer graph of this, but we'll see that we could have predicted a lot of the features. We see that it's going down on the left and up on the right. That's the end behavior. Okay, so that's coming from that part. We see that you see slicing through the y-axis just under 50. That's that 48 y-intercept. We do see that it hits the x-axis at minus 4 and 2. So that's cool. Here's something that we also could have predicted if we had looked a little harder at that square thing. Note that it doesn't across the x-axis at x equals 2, it only touches. There's a simple reason why that's true. If I'm looking at numbers near 2, well, if I'm looking at numbers near minus 4, the key is that it changes sign near minus 4. Let's see why that's true by going back to the factored form. Okay, if we go back to the factored form, this quantity, that definitely changes sign if I go through minus 4. For example, minus 4.1 plus 4 is minus 0.1. Minus 3.9 plus 4 is plus 0.1. So the 3 isn't changing, but as x goes through minus 4, this changes. Does this change? No. In fact, this never changes sign. It can never be negative. That's a square, right? X minus 2 squared is always greater than or equal to 0. That's a huge difference. This is a factor that can change sign and does change sign when it's 0 at x equals minus 4. This is a factor that can never change sign. It can just sort of touch 0 at 2 and then go back in the same direction. And that's why we get the pattern we see here with the graph, that here, the around minus 4, it's that x plus 4 factor that's really taking control, and it's changing sign. Whereas over here, the x plus 4 factor is not going to change at all. X plus 4 is going from 5 to 6 to 7. That's not changing sign. That's just positive. And the x minus 2 squared factor doesn't change either, because it can never change. What it does is it just touches and rebounds. Okay, so what we say here is that we say that the 0 at x equals minus 4 has multiplicity 1. That's the exponent it had in the factored form. Let me bring that factored form down one more time, so I don't have to keep scrolling up. So there's our form. This was x plus 4, did not want to do that, x plus 4 to the 1 power. It has multiplicity 1, and that's an odd number. And what that means is that it can change sign. It can and does change sign across that 0 or that root or whatever you want to call it. Okay. On the other hand, the 0 at x equals 2 has multiplicity 2. That's an even number. And anything, positive or negative, to an even power, that's never going to be negative, right? And so this cannot change sign. And that's why the graph of y equals f of x has a very different behavior. It just touches the x-axis. There, the x-axis at x equals 2, and doesn't cross. So that gives you an idea of a really interesting qualitative difference between odd multiplicity and even multiplicity. I've only shown you one example, so that doesn't get you all the variation. And there's interesting things you can say about, like, what's the difference between multiplicity 1 and multiplicity 3. But I'll leave that for the book and for us to look at in class, so that I can cut off this video at this point.